Thank you for your interest in our paper, SPG, and Supervised Domain Adaptation for 3D Object Detection via Semantic Point Generation. Our study aims to improve 3D object detection in the setting of unsupervised domain adaptation. Unsupervised domain adaptation aims to generalize a model to a novel target domain by using labels only from the source domain. The two domains are generally related, but there exists a distribution shift. In our case, the different point cloud quality. To eliminate the domain gap, our method, semantic point generation, recovers the foreground area by generating semantic points combined with the original cloud. Those semantic points can directly be used by any LiDAR-based detectors and help improve the detection results. Firstly, to understand the domain gap, we study the Waymo domain adaptation dataset, in which the Waymo open dataset is the source domain, and the Waymo Kirkland dataset is the target domain, which is collected with the same LiDAR sensor but in different locations and environments. If we train a detector on the source domain and evaluate it on both domains, we can observe a 21.8% performance drop on the target domain. After ruling out other factors, we find OD are mostly collected in dry weather, but Kirk are mostly in humid weather. Based on the weather labels, we separate Kirk into Kirk dry and Kirk humid. We find there is no performance drop on the dry frames, but only on the humid frames. Adverse weather condition causes a missing point problem. We find the missing LiDAR signal is doubled in the humid frames and significantly reduce the coverage of the foreground objects. To overcome the missing point problem, we propose a method, semantic point generation, to recover the foreground areas. SPG voxelizes the point cloud and predicts the confidence score for voxels that if they are in the foreground regions. After applying a probability thresholding, we add a semantic point and the predict location in each of these foreground voxels. The generated point feature includes the XYZ location and the point properties. These semantic points are merged with the original point cloud and fed into the 3D detector. Our method can work with any LiDAR-based object detector without any change of the detector's architecture. To supervise SPG, we create training targets of class label, which indicates if a voxel is inside the foreground bounding box, and regression target of the semantic point location and the point properties. SPG includes three modules. Voxel feature encoding module, which aggregates points in voxels and stack them into feature pillars. Information propagation module, which populates info in the occupied pillars into neighboring pillars. Point generation module, which maps the pillar features back to voxels and generates semantic points. SPG also employs two important strategies to recover the missing points. The first strategy is hide and predict. During training, we randomly select voxels and hide their points to mimic the missing point problem in the source domain, and still require SPG to predict them as foreground voxels and generate semantic points. To further encourage points recovery, we employ semantic area expansion, in which we expand the generation areas to the neighboring empty regions. We supervise the out regions within object bounding box to be foreground regions. This strategy allows us to predict semantic points in the expanded empty regions, which result in 5 times more semantic points on foreground objects. These are some visualization of the semantic points. We conducted experiments on the Waymo domain adaptation dataset and the KITTI dataset. We also combined SPG with two representative detectors, point pillars, and PVR-CNN. In the unsupervised domain adaptation task, SPG improves both detectors on the source domain and the target domain. SPG also improved detectors on general 3D object detection task. By the time of the submission, SPG with PVR-CNN ranked the first on the KITTI testset benchmark and surpassed all the state-of-the-art detectors. We have also compared SPG with other strategies that targets deteriorating point cloud qualities. Ablation studies have shown the effectiveness of the strategy hide and predict and semantic area expansion. SPG is also very efficient, only adding 16 millisecond latency on detectors. Thank you. Please visit our poster section for more details.